Hey everyone, and welcome to The Explainer. Today we're taking an absolutely breathtaking journey, and it's all based on a really fascinating conversation between astrophysicist Neil deGrasse Tyson and particle physicist Brian Cox. We are going to zoom all the way down to the absolute smallest subatomic building blocks of nature, and then we're going to pan all the way out to the extreme edges of our universe. From the invisible forces that bind us together to extreme alien environments right in our cosmic backyard that could actually harbor life, we're basically deconstructing reality itself to understand how the whole shebang works. Let's dive in. To properly frame our journey today, consider this fantastic quote from the legendary physicist Richard Feynman. He said, "Science is a satisfactory philosophy of ignorance." We often think of science as just this big, heavy textbook of facts, but it's really the exact opposite. It is a duty to boldly embrace the unknown. You start from a position of simply not knowing, and then you use a really rigorous process to acquire reliable knowledge. Nature is the ultimate judge, jury, and executioner here. And to see exactly how we question nature, we have to start incredibly small. Section 1. The micro. Smashing protons at CERN. Okay, so to deconstruct reality, scientists need the ultimate microscope, and that is the Large Hadron Collider, or the LHC, located over at CERN in Europe. This is the world's premier particle physics laboratory. It's just an incredible feat of international engineering designed to peek inside the fundamental building blocks of matter. But to truly appreciate it, you have to wrap your head around the mind-blowing scale of what actually happens inside this machine. The LHC is a massive ring. It's about 27 kilometers, or roughly 17 miles around. Inside this ring, protons are accelerated using these massive magnetic fields until they are traveling 11,000 times a second around that giant track. That means they are moving at 99.999999% the speed of light. Absolutely wild. And this brilliantly illustrates exactly how particle physicists actually do their jobs. First, you get those protons moving at near light speed. Second, you smash them together. Now, you might think you're just breaking the protons apart to see what's inside, right? Kind of like smashing a chair to see the wood. But actually, the third step is where the real magic happens. Using Einstein's famous equation, E equals mc squared, scientists use the massive energy generated from that collision to spontaneously manufacture entirely new, incredibly massive particles out of pure energy. Particles like the famous Higgs boson. Finally, because these massive particles only live for a tiny fraction of a second, the fourth step is using these giant complex cameras to detect the debris they leave behind as they decay. Section 2. The fundamental particle zoo. By sifting through all of that subatomic collision debris over the decades, we've slowly built up an inventory of the universe. And it's remarkable how fast we've zoomed in on this particle zoo. I mean, for thousands of years, going all the way back to the ancient Greeks, we theorized about this indivisible atom. But think about this timeline for a second. It wasn't until the turn of the 20th century that we actually proved atoms had a dense nucleus. By the 1930s, which is almost within living memory, we realized that nucleus was actually made of smaller protons and neutrons. And then, by the 1960s, using those higher energy collisions, we found that protons and neutrons were made of even smaller, point-like objects called quarks. So think about the precise pattern we've discovered in our fundamental inventory. As far as we currently know, literally everything in the universe is made from these specific building blocks. You and I, we're made mostly of up and down quarks, which build our protons and neutrons, plus some electrons. But nature doesn't just stop there. It gives us two heavier copies, or generations, of these particles. We've got the charm and strange quarks, the top and bottom quarks, alongside heavier versions of the electron called the muon and the tau, and their elusive neutrino counterparts. So that's 12 fundamental matter particles. Add in the bosons, which are the particles that actually carry the forces of nature, like photons, gluons, and the Higgs, and you basically have our entire known universe. But here's a really profound mystery. Why on earth are there exactly 3 generations of these matter particles? Honestly, we still don't have the answer to that. So we have our subatomic building blocks sorted out, but a universe just full of unattached floating particles is incredibly boring, right? So what are the rules that cause these particles to interact? What forces bind them together to form stars, planets, and, well, us? Section 3. The invisible forces and dark gravity. As we shift gears from the microscopic realm up to the macro scale, we really have to look at the invisible architecture of the cosmos. Now, we understand electromagnetism, the strong nuclear force, and the weak nuclear force quite well in the quantum world. But there is an enduring, totally fascinating mystery hanging out there. gravity. To understand why gravity is so weird to physicists, consider this. Gravity is tremendously weak compared to electromagnetism. If you reach down and pick a ball off the floor, the electromagnetic force in your muscles is effortlessly defeating the gravitational pull of the entire planet Earth. No contest. But here's the catch. Electromagnetism can cancel itself out with positive and negative charges. Gravity, on the other hand, is purely additive. It only ever adds up. So, on massive cosmic distance scales, it completely and totally dominates the universe. And our observations of gravity on that massive scale have revealed something entirely unexpected. We look out at galaxies and we see them spinning way, way too fast for the amount of visible stuff that's actually inside them. Now, for decades, you've probably seen headlines talking about dark matter, which implies there's this massive amount of invisible physical substance out there that we just can't see. But a far more scientifically accurate term is actually dark gravity. We don't actually know if it's a new particle or matter at all. What we know for a hard fact is the measurement itself. The gravity we observe simply doesn't match the matter we see. The galaxies are spinning too fast. It's a dark gravitational mystery. Section 4. The macro. Black holes and horizons. Now, if you really want to study gravity, you have to look where it's at its absolute most extreme. Black holes. These are the regions of the universe where physics is pushed to its absolute limits, right where general relativity and quantum mechanics intersect. Over a century ago, back in 1916, Carl Schwarzschild calculated the mathematical possibility of a black hole, just months after Einstein published general relativity. It started as pure math. You can't see inside them, of course, because of the event horizon. That's the boundary where gravity is so intense that not even light can escape. But today, we've moved from pure theory to incredible, tangible observation. We are literally mapping the massive magnetic field surrounding them, observing the colossal jets of material they eject out into space, and incredibly, we are now detecting the actual ripples in the fabric of space-time caused when massive black holes collide with each other. We are finally probing the most mysterious objects in reality. Section 5. Oceans of Europa. But, we don't actually have to look to the deepest, darkest corners of the cosmos to find thrilling frontiers. Right here in our own solar system, a profound search for extraterrestrial life is underway. Have you heard of Europa? It's one of Jupiter's moons, and it is a prime candidate for a habitable world. We are almost certain that it has a massive, stable saltwater ocean hidden beneath its icy crust, holding more water than all the oceans on Earth combined. But out that far from the sun, you might be wondering, why isn't it just frozen solid? Well, it's the intense gravitational squeezing from Jupiter itself that literally heats the moon and keeps that ocean liquid. And it gets even better. Material spewed from the nearby hypervolcanic moon Io may land on Europa, get irradiated, and then seep down into that ocean, acting almost like a chemical battery. It's an incredibly stable, complex system that's been untouched for billions of years. It's honestly the perfect habitat for harboring simple life. When you stop and think about the vast, complex chemical interactions happening in those dark, alien oceans, there's this poetic quote that I think really captures the essence of it. Life is an electron looking for a place to land. At its most fundamental, origin-level state, life is really just complex chemistry. It's electrons moving around trying to find stability. And in the deep, warm, saltwater oceans of Europa, countless electrons might just be finding their landing spots right now, sparking the beginnings of single-celled organisms that are completely independent of our own tree of life here on Earth. How cool is that? Section 6. The Human Skill. Fragile Lives, Infinite Universe. We have traveled all the way from the microscopic domain of quarks and particle accelerators to the dark gravity of spinning galaxies, the event horizons of black holes, and even the icy alien oceans right here in our solar system. When you zoom out and really look at the sheer scale and complexity of it all, the science inevitably bleeds into philosophy. So I want to leave you with this lingering question to chew on. What does it actually mean to live a finite, fragile life in an infinite, eternal universe? Science is a brilliant, totally necessary light that gives us the framework of reality. It maps out the quarks and the cosmos. But science alone doesn't hand us our meaning. That is the grand, beautiful mystery that each of us, as brief, conscious observers of this massive universe, must explore and answer for ourselves. Keep wondering, keep exploring, and I'll catch you in the next explainer.